Hello everyone, I am Sweta from GMRP Gajwel. In this class, I am going to basic radar range equation and range performance factors from radar equation. Okay, so previous class we have discussed about the radar and its basic principle and classifications of radars and radar block diagram and its functions and applications and uses of radars we have discussed. So now in this topic you will learn the derivation of the basic radar range equation and its performance factors. Okay, so first of all, we have to assume while deriving the radar range equation, first of all, the target is isotropically radiating. Means isotropically means it in all the directions the target is radiating. Next, target area is constant and the target is stationary and no other objects are present near the target. Weather conditions are fair, that is no dust or smoke or rain, etc. So we have to assume all these conditions. Okay. First thing is target is isotropically radiating. That means in all the directions the target will radiate. Next, the target area is constant and target is stationary. Next, no other objects are present near the target. Last condition is weather conditions are fair. That means no dust or smoke or rain or anything. Okay, so weather condition is fair. We have to assume all these conditions. Okay, for deriving radar range equation. Okay, so first of all, so if we have to determining the maximum range at which any target can detect. So here the radar range equation is used for determining the maximum range at which any target can detect and understanding the factors affecting the radar performance and design of radar system. So these three are the uses of radar range equation. So here in order to deduce the maximum range of a radar set, it is necessary to determine the power of received echoes and compare it with minimum detectable power of the receiver and that can handle and display satisfactory. So first of all, we have to determine the power of the received echoes. Okay, first of all we have to determine the power of the received echoes. Okay, first of all we have to consider the power density of the isotropic antenna, that is omnidirectional. So here this is the radar set and in that moving object is here and maximum range. So first of all, let the peak transmitted power be, we have to assume that the peak transmitted power be PT and antenna is isotropic. That means it radiates the energy in all the directions. Next, then the power density at the distance d from antenna is given by PD is equals to PT by 4 pi d square, that is equals to radiated power by surface area. So here the power density PD is equals to radiated power by surface area. So here the radiated power is PT and the surface area is 4 pi d square. Okay. So here the surface area is an imaginary sphere of radius r. So here see here, so power density equals to transmitted power by surface area of the spherical region. So therefore PD is equals to PT by 4 pi d square. Okay. So next, but the antennas are directional rather than the isotropic. Therefore, power density at the target is equals to PT is equals to APPT by 4 pi d square. Okay. So here is the maximum power gain of the antenna. Next, the power intercepted by the target will depend upon its radar cross section or effective area S. So then the power falling on to the target will be PD is equals to S into AD PT by 4 pi d square. So here S is the power intercepted by the target will depends upon its radar cross section area or effective area. So here S is a radar cross section area or effective area. Okay. So next, the power falling on the target will be is equals to PD is equals to S into AD into PT by 4 pi d square. So here, but the target is not an antenna and therefore its radiation may be thought of isotropic, that is omnidirectional. So accordingly, the power density of the receiving antenna will be S into ADPT by 4 pi d square into whole square. So adanta kuda manaki enti transmitting antenna. So coming to receiving antenna, PR is equals to S into ADPT by 4 pi d square whole square. So here the square in the denominator due to spherical area concept of the surface density. Okay. So here the receiving antenna will intercept only a portion of the radiated power that depends upon the cross-sectional area or capture area of the receiving antenna. So in the previous transmitted power we have considered only as that is a cross-sectional area of the antenna. So here we have to consider the A0 also. This is the cross-sectional area or capture area of the receiving antenna. So therefore the received power is given by PR is equals to A0 into SADPT by 4 pi d square whole square. So if the same antenna is used for both transmission and reception, the maximum power gain is given by 4 pi A0 by lambda square. Here the lambda is the wavelength and we have already PR is equals to A0 S APPT by 4 pi d square whole square. Okay. So here we have to apply again. We have AD is equals to 4 pi into A0 by lambda square. So substituting the equation in that we will get PR is equals to PT A0 square S by 4 pi d to the power of 4 lambda square. So here we have to determine the maximum range equation, that is Dmax. So that is observed when the received power PR is equals to the minimum receivable power of the receiver. So that is equals to PR is equals to P minimum. So from this equation substitute here D is Dmax and separate it into the left side of the equation. We will get Dmax is equals to Pt A naught square S by 4 pi P minimum into lambda square. So here we are applying Pr is equals to P minimum to the power of 1 by 4. Okay. So from all these equations we have a maximum range radar equation is Dmax is equals to Pt A naught square S by 4 pi P minimum lambda square to the power of 1 by 4. Okay. If A naught is equals to AD lambda square by 4 pi, then Dmax is equals to Pt AD square S lambda square by 4 pi 3 P minimum into 1 to the power of 1 by 4. So either, therefore the maximum range covered by a radar system is given by Pt A naught square S by Pt A naught square S to the power of 1 by 4. Okay. So here the performance factors of the radar range equations is so here the maximum range of the radar will varies as fourth root of the peak power transmitted, that is to the power of 1 by 4. Okay. And therefore to increase the twice transmitting power must be enhanced to 16 folds. Okay. So but to increase the range by 3 times, the transmitting power must be increased to 81 times. So here the range is inversely varies as receivable power. Okay. So P is inversely varies to radar range equation. So therefore to increase the range, minimum power detectable by radar must be reduced by increasing the gain of the receiver. But the radar will be subjected to jamming and interference. Okay. Here the range is proportional to the power gain of the antenna, which is proportional to the diameter of the parabolic dish antenna. See here the range is directly proportional to the power gain of the antenna. Here the D is the diameter of the dish antenna. So therefore the range can be increased by increasing the diameter of the parabolic reflector. Next, this maximum range also depends upon the target area also. The maximum range is proportional to the square root of the capture area of the antenna. Therefore, the range can be increased by increasing the frequency of operation also. Okay.